So let's start with an example, guys. Okay, start with an example. So we're going to do a little bit of counting principle. You need counting principle. It's not a very difficult concept for two things. Firstly, you will need it to do some probability problems. And then when we do combination and permutation, you will need it as well. All right, so what's going on here, guys, is let's say you can choose, you're at a pizza restaurant and you're buying pizza. You have two types of crusts, deep dish and thin crust. TC stands for thin crust, deep dish, DD. And you have three types of toppings. Okay, you get to choose only one topping at a time. Sausage, pepperoni, hamburger. How many pizzas would you get? Would you order? Well, the answer is very simple. With your thin crust, you will get, now we call it a tree diagram. It's a little hard. With your thin crust, you're going to get this, this. With deep dish, you're going to get this, and this. What does that really mean? Well, for your thin crust, you can get thin crust with sausage on top, thin crust with pepperoni, thin crust with hamburger on top. Or you can choose deep dish, same three choices for your topping. So basically, how many different pizzas can you order? Well, let's find out. How many choices do you have for the uh, crust? I'm going to write crust. Let me do it a little differently. How many choices do you have for the crust? Two. How many choices do you have for the topping? Three. Okay. And you multiply. This is called counting principle. Okay. You can choose a crust in two different ways. You can choose a topping in three different ways. How many ways can you do both? Well, the answer is 2 times 3 is equal to 6. This is called the fundamental counting principle. Okay. It works a lot better when you use an example. Here's another example for fundamental counting principle to illustrate fundamental counting principle. And this will, I think, come up again. So here, let's say you're rolling a six-sided die and tossing a coin, okay? Your die could give you a 1, 2, 3, 4, 5, 6. But you're tossing a coin at the same time. Your coin could give you an H or T, head or tail. So your total sample space is going to be this. This is going to be your sample space. You're listing it a little differently. You could get one with the head, one with the tail, two with the head, two with the tail, three with the head, three with the tail, four with the head, four with the tail, five with the head, five with the tail, six with the head, six with the tail. So again, you can use the fundamental counting principle to find out how many there are. Of course, you can count. You can say your die. How many choices do you have for the die outcome? I would say six. How many choices would you have for the coin outcome? I'm going to say two. And if you do that, your answer is going to be 6 times 2 or 12. There are exactly 12 outcomes. Your sample space has 12 elements. All right, this is another good example, and your book has a lot of problems based on this. So what are we doing here? Now, instead of rolling a die and a coin, we can roll the same die twice. Let's say, and to make things a little more clear, we are using two colors. Let's say you're rolling a blue die and a red die. Your blue die has a 1. It can be paired up with 1 from the red, 2 from the red, 3 from the red, 4 from the red, 4 from the red, 6 from the red. It can be paired up with 6 of the red outcomes. If you're blue, if you get a 2 on your blue die, that can be paired up with 6. 1, 2, 3, 4, 5, 6 from the red. 3, 1, 2, 3, 4. So again, how many ways can you get a blue outcome? There are 6 ways you can get a blue outcome, right? I'm gonna make it bigger and you'll be able to see in a second. Okay, your blue die has 6 possible outcomes. Your blue die has 6 possible outcomes. Your red die has 6 possible outcomes. And how many ways can you get a blue and a red? Well, simple as before, 6 times 6 or 36. Now, if you carefully count your sample space, there are 36 items here. 1, 2, 3, 4, 5, 6. Each pair is an outcome. 6, 1, 2, 3, 4, 5, 6. If you multiply 6 by 6, you get 36. Now, the question will say how many ways can you get a sum of 1? Well, you will never get a sum of 1 because if you get 1 and 1, that's going to be, let me make it a little bigger. That'll be 2. So if you're rolling 2 dice, what's the probability of getting a 2? You can get a 2 only one way out of 36. So the probability is 1 over 36. How many ways can you get a 4? You can get a 4 by in 3 different ways. Right here. 3 and 1, 2 and 2, and 3 and 1. Now, there is a distinction between a 1 blue and red 3 and 3 on the blue die and 1 on the red die. So 3 different ways you can get 4. That's why the probability of getting a 4 is 3 over 36. So you will see these lines, they add up to 5. These numbers on this line add up to 6. These numbers along this diagonal, they add up to 7. And then it's 8. These numbers add up to 9, 10, 11, and 12. What's the probability of getting 11? Well, you can get 11, 5, 6, and 6 fives. That's the probability. What's the probability of getting a 5? 1, 3, 4, 5. 1, 2, 3, 4. 4 different ways you can get a 5. 4 out of 36 is the probability of getting a 5. Again, when you're rolling 2 dice, we will generally be talking about the sum of the outcomes. So fundamental counting principle, we have actually seen 3 examples of fundamental counting principle, but let's define it formally. A fundamental counting principle means if you can choose task A, if task A can be done in 5 ways, task B can be done in 3 ways. How many ways can you choose task A and then task B? 5 times 3, 15. Suppose you have 5 shirts to choose from and 3 pairs of pants to choose from, and you're going to wear a shirt and a pair of pants. How many different outfits can you have? 5 shirts times 3, 15. Let's write it down. 3 times 5. 5 shirts, 3 pants. How many outfits? 5 times 3 based on the fundamental counting principle. And there are tons of examples here. You can take a look. It's hard to draw. Okay. What are independent events? Okay, 2 events. I'm not going to worry too much about the sets. So two events are independent if the occurrence of one event doesn't change the probability of that the other one occurs. What does that mean? Well, when you're rolling a die and tossing a coin, they're independent events. They have nothing to do with each other. So getting a six will not have any impact on getting ahead on your coin. Two events are independent if their probabilities are not influenced at all. All right? And here are some examples. So let's do an example. You have examples like this in your book. Let's do one. It's a very typical probability question. Okay. Suppose you have two bags, bag A and bag B. Bag A contains two blue marbles and a red marble. So let me make a table, okay? So I'm going to do it by hand. It is in our notes. Okay. So the first one, I'm going to list it horizontally, a blue one. They're identical. Unfortunately, I'm going to delete this. Let me try it again. Two red, one blue, and bag A has two and one, two and one. Okay, we need a 3 by 4 by 4. So I'm going to first draw the sample space. Draw a sample space. The first one, this is my sample space is going to be here. It's actually based on the tree diagram, and it's kind of like the two rolling two dice. Okay, the two dice we rolled were identical. Here they're a little different. Bag A is going to be horizontal. Okay, so I have two blue marbles. I'm going to make sure you can see the whole thing, and a red marble. And it's kind of important to be consistent how you write it. And two red marbles here. You start with red marble, two red marbles, and one blue. Okay. Now the yellow part is where you're going to list your sample space. Now you will draw a marble from from bag A first, then you'll draw a marble from bag B. This is your bag A. Okay. So this is your bag A, and this is your bag B. Okay. If you draw a marble from bag A, you could get B, the first blue marble, or the second blue marble. Yes, they're identical, but you have to account for it because it'll have an impact on probability. You just can't say, oh, they're identical, so I'm just gonna pretend there's only one. You can't say that. Your first blue marble can be paired up with the red, or the second red, or the blue. The second blue marble, same kind of a deal. BR can be paired up with this red, can be paired up with this red, can be paired up with this blue. Your red, 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 and blue. This is your sample space, the yellow part. All right. Now, what did they say? List all the possible outcomes. Sure. I just listed it. Okay. This is the list of all possible outcomes. Now, let's focus on this and see if we can answer some questions. I think your notes has some questions, but I'm just going to make something up. What's the probability if you're drawing a marble from bag A, then a marble from bag B? What's the probability of getting two red marbles? Answer is going to be 2 out of 9. Okay. Probability of getting RR, two red marbles, is 2 nines. The sample space has 9 listed outcomes, and only these two are called the favorable outcomes, right? We are finding the probability of these. What's the probability of getting 2 red marbles? Well, 2 out of 9. What's the probability of getting 2 marbles of different colors? See if we can do that. What's the probability of getting 2 different colors? Probability 2 different colors. And that's going to be BR, 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 RB. Don't forget this. That's 5 out of 9, right? Probability of getting 2 marbles of different colors is 5 out of 9. Okay. All right. We have a couple of examples, I think. And you can take a look at this example here. It's the same thing. So when you roll 2 dice, my first example had dots. That's a little hard to draw, but you can always on the exam draw your sample space for 2 6-sided dice. 2 6-sided dice as 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. So it's a little easier to manage when you're taking notes or when you're writing something during your exam. Okay. So I'm gonna see how I do this. I'm gonna just take my slides from here. See if we can work on this one. This is also a problem, I think, from your book. Something very close to it. So what the art is saying, suppose you have a bag that contains 1 blue marble, 1 red marble, 1 green marble. You will draw a marble from the bag, record the color, and then put it back. It's called width replacement. So you draw it from the same bag twice, but with replacement. And you're trying to find the possible outcomes or sample space. Now, I have the sample space here. So you could get a red, blue, green from the first draw. Since you're putting it back, you can pair the blue with the blue, or blue with red, blue with green. Same thing. This is your sample space. You really want to analyze it. So if you, let's say you pick up this blue and put it back, it'll be paired up with this blue, this red, this green. If your first draw was this red, it'll be paired up with this blue, this red, and this green. So this area is your sample space. This is your sample space. Okay. Now, let's say we want to find the probability of getting 2 blue marbles. There are altogether 9 outcomes listed in my sample space. Only one outcome shows 2 marbles. So the answer is 1, 9. What's the probability of getting 2 red marbles? There are 9 outcomes in my sample space. Only one has 2 red marbles. So 1, 9. What's the probability of getting 2 green marbles? 1, 9 again. What's the probability of getting 2 marbles of 2 different colors? It's not here, but we can do it. 1, 2, 3, 4, 5, 6. It'll be 6 over 9 or 2/3. Now, let's do an interesting problem. All right, it's the same problem, okay, but there's a subtle difference and you want to really understand that, okay? It's a very similar problem. So let's read this. You have the same situation, 1 blue marble, 1 red marble, and 1 green marble. You'll draw a marble from the back, record the color, and then hang on to it. It's called without replacement. Okay? So I don't need this anymore. Okay. Now I'm going to show you, just ignore this. Okay. This is not valid anymore. So we will pretend it's with replacement. You're putting it back. So the first blue marble that you got, Since you put it back, it can be paired up with the blue marble. You just pretend when they give you without replacement scenario, you for 1 second, you pretend it's with replacement. And all you have to do is ignore this or cross it out, cross out this diagonal. And the leftover is your true sample space. Since you never, when you got blue and you never put blue back, blue will never pair up with itself. You'll get a blue red or a blue green. If you get, since it's without replacement scenario, you never put the red one back. Red one will be paired up with blue, red one will be paired up with green. Same thing, you didn't put the green one back. Green one will be paired up with blue, green one will be paired up with red. Now it's the same thing. If they ask you what's the probability of getting two, well, let me show you what's going on here. So really, your sample space, once you remove that very diagonal, very carefully, because blue can never be paired up with blue, red can never be paired up with red, green can never be paired up with green because the marbles were not put back. So your sample space now has only 6 points. 1, 2, 3, 4, 5, 6 points. Six points, okay? Now, if they ask you what's the probability of getting a blue and a red marble, that'll be 2, 1, 2 out of 6. What's the probability of getting a red and a blue marble? It'll be 2 out of 6. What's the probability of getting two red marbles? Well, you'll never get it, so it'll be 0. What's the probability of getting two green marbles? You'll never get it. Green will never pair up with itself, so it'll be also 0. Okay, I hope that makes sense how we remove the diagonal. That's very important. That's a very important uh, point. Okay, we're going to stop here and we will do conditional probability a little later. It's a little messy. Okay, that's the last section we have. So we're going to stop here for today. Conditional probability is coming up.